Hey, good morning, everybody. This is Mr. Ainsworth. We're going to do a little mind mapping on all types of asymptotes, and I'm talking about the three different types: the vertical, the horizontal, and the slant. Okay, so get a blank piece of paper here, or do this on your iPad, whatever you like. Let's start off with some graph paper just to make things a little bit easier, or if you prefer blank, that's cool too. All right, and grab your red pen and let's put the word asymptotes right in the middle. Okay, and we're going to do a little mind mapping on this concept here. Okay, so asymptotes. Okay, there we go. And we have three types. Okay, we're going to start off with the most basic type, and then we're talking about vertical asymptotes, and we're talking about dealing with rational functions here since we were in that unit on rational functions. So let's take it off to the side. Let's go to the upper right. Doesn't matter where you put this here, but let's put the title at the very top. Okay, vertical asymptotes. There's three types. All right, and make sure you spell it correctly too, because guess what? Spelling is important too in mathematics, even though we're in mathematics. Okay, so here's the concept. All right, in terms of rational functions, okay, where you have a quotient of two polynomials, okay, that's a lot of words right there. Okay, it is where the function is undefined because you cannot divide by zero. So here's the key concept here. All right, where, all right, is the function undefined? That's what you have to figure out. Okay, it's where the function's undefined. Why? Well, it could because you cannot divide by zero. You never have, and you guess what? You never will too. Even I can't divide by zero. Okay, you cannot divide by zero. That's the reason why. All right, let's take some examples. Okay, and again, mind mapping is all about brainstorming about all the different key concepts of a topic, and we're talking about asymptotes in this topic. All right, so let's take an example. All right, you got to take an example to work with something, right? So if f of x here is equal to a very simple rational function, let's take I don't know, 2x divided by x minus 4, let's say. All right, it's undefined at 4 because 4 minus 4 equals 0. Okay, the denominator, okay, is what you're dividing by. You're dividing by x minus 4 here. All right, that cannot be equal to 0. So we say that the vertical asymptote is at x equals 4. Okay, we have vertical asymptote VA, okay, at x equals 4 because 4 minus 4 is 0, and that's where the function is undefined. All right, that's as simple as that right there. We're talking about vertical ones here, not horizontal, not slant. Okay, we're not talking about holes either here. We'll get to that topic here in a minute. Now we call these non-removable discontinuities because you cannot simplify the function anymore, and because of that, it's undefined at 4. Okay, f of x here is undefined, all right, at x equals 4. That's why we have vertical asymptote, and because it's called a non-removable discontinuity. You can't simplify it. You can't remove it. Okay, that's the reason why. Okay. Now let's do it again. Okay, so because we have different functions possible, so let's brainstorm a little bit more. So if it's a little bit more complicated, so let's say we take a different function g of x here. Let's say we have x minus 1 divided by x minus 1 times, I don't know, 2x plus 3, let's say. Now notice here we can simplify a little bit. Okay, we can simplify here, and it's undefined at 1 here. Okay, the function is undefined at 1. It's also undefined where 2x plus 3 is equal to 0. That happens to be at negative 3 halves. All right, but we don't have a vertical asymptote at 1. We have vertical asymptote wherever the function's undefined in the other term here. So let's simplify it a little bit. All right, we get 1 divided by 2x plus 3. Okay, so right here we have a hole. I'll talk about holes more in a minute here. This is a removable discontinuity. So we have a hole at x equals 1 and not a vertical asymptote. And if you substitute 1 back in the function, in the simplified function here, you get 1 divided by 2 times 1 plus 3, which is 1/5. So we have a hole at 1/5. But more importantly, we're talking about vertical asymptotes here. And remember, 2x plus 3, that can't be equal to 0. So 2x cannot be equal to negative 3, and that means x cannot be equal to negative 3 halves. This function is all reals except 1 and negative 3 halves. So that tells me I have a vertical asymptote at -3/2. Okay, because the function can't, you can't divide by 0, and -3/2 would make that function equal to 0 in the denominator, and it's undefined there. Okay, you can't divide by 0. So we have a horizontal asymptote at -3/2. We have a hole at 1, 1/5 because we could remove that. So holes are not are called removable discontinuities. Okay, so this is called a removable because we were able to simplify it. Okay, discontinuity means that the function is not defined there. Like if we looked at the graph of this function here, you would not be able to trace the function through 1, 1/5 because it's undefined at that point, and you would not be able to trace the function with a pencil and -3/2 either because there's a vertical asymptote there. Go ahead and enter this in the TID4 Desmos, and you'll see what I'm talking about. Okay, so let's write down the key concept here that you need to remember. Okay, vertical asymptotes are called non-removable discontinuities. So grab your red pen. Vertical asymptotes are called, all right, non-removable. And again, all of this information is in your lesson. So go ahead, and I encourage you guys to take a look at it here because we went through it already. They're called non-removable discontinuities, all right, because you cannot simplify the function to remove the discontinuity. That's the reason why. Why? Well, let's ask a rhetorical question. Why? Well, you cannot, all right, remove the discontinuity by simplifying. Okay, look right up here. So this portion here, and I'm talking about this function right here, you can't simplify 1 divided by 2x plus 3. You can simplify the original function, but not the simplified function any further. Because of that, we have a vertical asymptote at -3/2 as opposed to a hole. So that's what you have to get together here. When it comes to asymptotes, right here, the first type that you look for are vertical asymptotes, where the function's undefined and you can't remove it. If you can remove it, like I showed you in g of x example here, the second one here, you may have a hole, you may not, okay, depending on if you can remove it or not. And if you can't, it simply becomes a vertical asymptote. And of course, you check with some graph and utility. Okay, now next topic here. Now I'm going to stem off, I'm just going to talk about holes again because these are the removable types. So let's go down here and let's talk about the removable discontinuities. So removable discontinuities. Continuities. Okay, we're talking about the big concept of what it means to be a hole. It's an infinitely small point on the graph where the function is undefined, but in this case, it can be removed by simplifying. Okay, so you have a hole. Here's the key concept. Or a hole exists. Let me put it that way. Okay, here we go. A hole exists. Okay, when you can remove the discontinuity by simplifying. Okay, and that's the key idea. All right, so let me give you an example here. Let's take a function here, and this is why mind mapping is so good. You take a function that you can show that a hole exists. So let's take this one here, x plus 2 times x plus 5 divided by x plus 5 times, something different. How about x minus 1? So you have this rational function here. All right, notice that the x plus 5s, these binomials, can cancel out. So right away, you have a hole at -5 because it's undefined at -5. It's also undefined at 1. Okay, but here, all right, you can remove the discontinuity. So notice that term, remove the discontinuity. All right, and so we have a hole here at wherever it's undefined. In this case, it's undefined at -5. All right, so -5 comma what, right? So what you do is you simplify the function. So I get x plus 2 divided by x minus 1. There's your simplified function. And now you evaluate the simplified function at -5. And guess what? We call that f of -5. And so -5 plus 2 divided by -5 minus 1 gives you -3 over -6, gives you positive 1/2. And so you have a whole at -5 comma 1/2. You just substitute the x value in the function and get a y value. You do what you always have done, ever since Algebra 1. Okay, so the first type of asymptotes we were talking about here were vertical asymptotes. The second type, which were called, let me go back, vertical asymptotes were called uh, non-removable discontinuities. Okay, right here, non-removable discontinuities. The second type of asymptotes we're going to talk about are the removable type, in which case you have a hole. And so if you can simplify it somehow and remove the discontinuity where it's undefined, all right, to get a simplified function, you have a hole. And this function here, the second function that we're talking about, f of x, it has a hole at -5 and also has a vertical asymptote at 1. Okay, so let's make a note of that. Vertical asymptote at x equals 1 because it's non-removable. So you guys have to clearly understand, what type you're dealing with here. And then no matter what function I give you, you just respond. Okay? And it's that simple. There's only, those are the two main types. And then of course we have the horizontal, and then we also have the slant. Okay, so let's talk about those. Okay, so let's see. I need to do something here. I'm gonna do something cool here. I need more little room on the left. Okay, so let's just shift this over a little bit. That's what's cool having digital technology, man. You have an infinite page. Okay. All right, so let's talk about the horizontal type of asymptotes. So let's go off to the side, to the upper left, up here, and let's talk about the horizontal asymptotes here. Horizontal asymptotes. Okay, here we go. Now, so what we want to do is take a look at a few types. There's 3 different cases. Okay, 3 cases here when it deals with rational functions. So case number 1. Okay, let's take a function here. Actually, you know what? I don't want to get too technical here. But anyways, let's take f of x here. Let's say that we have 2x squared plus 5 divided by 3 minus, well, I don't know, how about 5x cubed right here. And what you want to do is focus in on the dominant terms, the ones with the highest degree. All right. Now, technically here, well, I'll tell you how to do it easily, and then I'll show you the reason why. Okay, so horizontal asymptotes are where we take the limit, all right, as x approaches infinity of the function, and then you see what you get. And if that equals a constant, all right, if it equals a constant, then a horizontal asymptote exists. But the easy way to do that, when you take a limit of this, is you look at the dominant terms. Okay, so up top is the 2x squared. Down below is a negative 5x cubed. Those are the dominant terms with the highest degrees. All right, and notice that the degree up top is less than the degree down below. All right, so because of that, we have a horizontal asymptote y equals 0. Okay, why? Well, because the dominant term is in the denominator, and the denominator is increasing faster than the numerator here. And because of that, if we were to take a limit, okay, and here's the real explanation. If you take a limit to infinity of this function, 2x squared plus 5x, and you took a look at it graphically when x gets extremely large, all right, you would get 0. It approaches the x-axis. Okay, the x-axis is the horizontal asymptote. That's why we call it y equals 0. But the simple thing is to do it is you just look at degrees. If the degree of the numerator, is less than the degree of the denominator, the horizontal axis, the horizontal asymptote is always the x-axis, which has a special name. It's called y equals 0. Second case is when the degrees are the same. So let's give you a different function here. So let's say we have 5x minus 1 divided by 2 minus, no, actually, let's go 2 minus 7x here. And then we took a look at this limit right here. So what is the limit as x approaches infinity of g of x? Okay, what is that limit? Well, you take a look at the dominant term scheme, the 5x and the minus 7x. And when you take a look at this limit here, because of the degrees are the same, they're both first degree here, it's going to be equal to the quotient of 5 and negative 7, which is equal to negative 5 sevenths. Okay, so the horizontal asymptote in this case is y equals 5 sevenths. Excuse me, negative 5 sevenths. And that's because they have the same degree. So when the function or the polynomial in the numerator is the same degree as the polynomial in the denominator, all you do is take a look at the lead coefficients and divide the lead coefficients. And then if you were to graph this horizontal asymptote y equals negative 5 sevenths in Desmos or the TID4, you would see that the function approaches it whether you go to negative or positive infinity. Okay. Now the third case, let's say we have the degree up top is higher. So let's say you have 2x squared minus 5x plus 1 divided by x plus 2, let's say. Notice that the degree up top is 2 and the degree down below is 1. All right, now when you take the limit, okay, as x approaches infinity of your function, let's just call it h of x here, the numerator is going to be increasing faster than the denominator, and this is going to be equal to infinity, which means it does not exist, okay, which means no horizontal asymptote, okay? If you take a look at the graph here, it does not have one. It has actually a slant asymptote, not a horizontal one. And those are the three cases. And that's all you have to study, okay? Case one, the numerator's degree is less than the denominator's degree. And it's always the x-axis here, y equals 0. Case two, if the degrees are the same on both top and bottom, numerator and denominator, you simply divide the lead coefficients. And in case three here, numerator's degree is higher than the denominator, in which it has no horizontal asymptote. It may have a slant, it may not, depending on the difference of degrees. It has to be equal to 1 to have a slant. So speaking of that, okay, the next type here is called a slant asymptote. So let's go ahead and take a look at that. Okay, slant asymptotes. Okay, now the condition here, okay, the degree of the numerator must be exactly 1 higher than the denominator. Okay, so let's make a note. Okay, so degree of the numerator must be, okay, exactly 1, exactly 1 greater, okay, 1 higher than the degree of the denominator. Okay, and that's a learning target, and we wrote that down in your lessons. And so, denominator, okay, and that's why I always tell you guys you have to go back and memorize your learning targets, because guess what? If you don't know them by heart, well, forget a homework problem. You can't do a homework problem. You can't do a quiz question. You can't do a test question. I don't care how simple it is. If you don't remember the idea, then you won't be able to do anything. So you guys better go back and study better so that you remember your learning targets, which is the most important things, because the numbers change on the functions and all the numeric stuff, but not the concept. The concept is the same, and all you have to do is apply it. So let me give you an example. Okay, so let's take a function here. Okay, I'm just going to make up a rational function. So let's say we have 3x squared plus 2x plus 1 divided by something 1 less degree. So top is 2 second degree, bottom has to be first degree. So let me just make something up here. Okay, divided by x plus 2. Okay, the way you get this, the way you get a slant, okay, your method, all right, is called a long division. Okay, long division. And all teachers talk about that. You can't say synthetic all the time, because if you divide by a monomial here, or excuse me, a binomial or something with a higher degree of 1, let's say 2, your long division or your synthetic division is not going to work. So you have to know long division. So let's Let's do it. Okay, we have to take 3x squared plus 2x plus 1, and then we have to divide it by, well, guess what? X plus 2, and let's see what we get. All right, so I'm going to do the steps over here. Okay, step number 1, you take 3x squared divided by x to get 3x. That goes in the quotient. And then you multiply, all right? 3x times x is 3x squared plus 3x times 2 is 6x. Now, technically you subtract, right? But I taught you guys how to add the opposite. All right, so just change signs and add, and you get negative 4x and bring down the 1. And then repeat. Step 2, negative 4x here. You always take first term divided by first term. And you get negative 4, so bring that up in the quotient. Step 2, multiply. Negative 4 times x is negative 4x. Negative 4 times 2 is negative 8. Grab your red pen and add the opposite. All right, and you get remainder 9. Okay, so that's equal to the remainder. So it's plus 9 divided by x plus 2. And then what you guys have to understand is that the slant asymptote is staring at you right here. It's the linear portion. So your slant asymptote, SA for short, in your notes, all right, becomes the linear portion, okay? Y equals 3x minus 4. It's a line, okay? It's linear. It's this linear portion here. And that's as simple as it gets, my friends, okay? If the degree up top is 1 higher than the degree down below, well, you have a slant asymptote. All right, and this, my friends, is everything you need to know about asymptotes. And this is called a mind map. And this is how you guys should study. You should develop one on your own using the examples in your notes or your homework that you know are correct. And then you put it together and you test your knowledge on everything that you should know about asymptotes, and you make one big, what's called mind map on one piece of paper. And if you can generate all this, well, guess what? You know it. All right, you know a lot actually. And then you're going to be doing much better in your exams because it's the concept that you need to remember, not the numeric part. I mean, the numbers are going to change, like I keep saying, but the concepts do not. So study effectively and learn how to study effectively here, so that you can do well in your exams. And you can apply this technique, by the way, to anything. This works in biology, physics, English, psychology classes. Like if you had a concept in psychology that had multiple different viewpoints, then a mind map would lend to that. Okay, check it out. It's called mind mapping. All right, I'm Mr. Aynesworth here. I'll see you in class. You guys take care. Study well. Study effectively. Okay, don't study hard. Study effectively like this. And I'll see you later. Bye bye.